Hi all, it's Mr. Yeager for chemistry. We are now looking at dilutions. All right, so we're continuing some of this solution math, and we'll just get going with it. There's not as much. Basically, we're just looking at a particular formula of how we generally start with a highly concentrated solution, and then we move to a more diluted solution. I'll give you a little bit more reasons in a moment why we would do that. But again, this presentation was created by another excellent chemistry teacher that I'm presenting with. So once again, our two definitions for telling us how strong a solution is. We have a concentrated solution, which means it has obviously a lot of solute, very little bit of solvent. We're going to see this using molarity. So we're going to have higher molarity values for concentrated solution, versus a diluted solution where you've added a lot more water to it, you've added more solvent, and therefore the molarity goes down because you're spreading those particles out. So to kind of already give you the idea of why this is really useful and important, okay, is a lot of times when, especially, I mean, we're just talking about in even a school, the chemistry teachers will order very highly concentrated acids or other chemicals. And that's useful because we can then use a little bit of that concentrated, add a lot of water, and now we have a ton of a lower concentrated solution. So it's a way to be very efficient in terms of how much you're using versus buying a lower molarity or concentrated solution where you might use it all up and immediately in a classroom. While, you know, in another one, we might only be using about 10 milliliters of the stock solution and making something ridiculous like, you know, 500 milliliters of that little bit of solution into something smaller that the entire students can use. So the equation is M1V1 equals M2V2. The M's are both molarities, the V's are both volumes. So you're going to see volume and molarity units here. Molarity, obviously big M, volume, liters or milliliters. Now for this, a couple things. You do not need to change the volume units unless they are different from each other. If they are the same, if they're both in milliliters, you can leave it. If they're both in liters, they can stay in liters. You don't have to be in liters like we have to be for molarity. Same thing goes when you try to answer it. You know, if we're solving for a final volume and I'm given both molarities and V1, whatever the unit for V1 is what the unit for V2 is going to be. So there's not a requirement that you have to change the units in this. Okay, the only time would be if they are both different from each other. Now, I want to write this out as well. While they kind of say M1 and V1 is your initial solution, molarity and volume, and M2 and V2 are your final volume and molarity, the biggest confusion that comes out of this I've seen with students is they mismatch which molarity to match up with which volume. They go, I don't understand which one's going together, or they just read the problem and they list everything in order, which that's not always correct. You could be correct, you could get lucky, but it's not always correct. So obviously, if you do read for context, you'll be good to go. But to help with that context, I usually give my students this version of the formula where I say MCVC equals MDVD, where C means concentrated. So you could sit there and go, if it says you have the concentrated solution and this is how much you have of it, of the volume, you can match those two up. Obviously, D's stand for diluted solution. Okay? So if that helps you out, use it. If not, throw it away and do the M1V1 and make sure that you're reading context very, very well. Okay? The MCVC is just to help with that context. So it says an experiment calls for 1 molar of HCl, but there's only 6 molar available. What volume of 6 molar HCl is needed to make 250 milliliters of 1 molar HCl? Okay? So what I have here is, again, if we read for context, it basically says I'm starting with this 6 molar HCl, and I want to change it to 1 molar. So 6 molar is my concentrated molarity. So that would, you could say my M1 if you want, or MC. It's asking for what volume of this do you need. So we are solving for, I'm going to write this out. I'm going to write it as my way, MCVC equals MDVD. Okay. if I'm writing this out, I'm solving for the volume of concentrated solution, okay? And they are giving you the volume and the concentration of the diluted solution. So this is where I see people make mistakes, because they'll sit there and be like, I got 6 and 250, so they go together, and then I got 1 and I'm solving for VD. No, that is bad reading, okay? That is a misinterpretation of the problem, and it is not really understanding what you are putting together here. So, reading it correctly, we are doing 6.0 times VC equals 1.0 times 250, and we solve. All right? And it's a pretty easy little equation to solve. You're basically going 1 times 250, so that's 250 on this side, equals 6.0 VC, and you divide 6.0 to the other side. So the volume of concentrated solution would be, I need, and I only want 2 sig figs, 42 milliliters of the concentrated solution. So what we mean by that, just again, give you greater context, what you'd actually do to create this solution is that means I have 42 milliliters of HCl, and the rest of the 250, which that would be what, 208 milliliters of the solution, is water. And so the correct way to do this would be add the water first up to 208, and then I'm going to add the 42 milliliters of acid. That's actually the safe way to do it. We actually always add the acid to the water, not the water to the acid. Okay? And so then it would create this 250 milliliter solution, which you kind of make sure that it's mixed well, and therefore you now have your 1 molar solution. All right, we're going to do just a couple more of these because there's not much to it. The chemist needs 15 milliliters of 0.5 molar. So these two things are together. The of also helps make sure that you understand what is connected. All right, but only has a 3 molar solution. So the 0.5 is my diluted. That would be my MD. This is my VD. And it says what volume of the 3 molar, which is my MC, my concentrated, it's the larger. Basically, I'm doing the same thing. 3.0, I guess I'll write it out again to make this nice easy. MCVC equals MDVD. I get 3.0 times VC equals 0.50 times 15. So it would be 0.5 times 15 divided by 3. My final, the volume that I need is 2.5 milliliters of the concentrated solution. And then the rest of it would be water. All right, let's see if it changes it up at all. That's the same thing. That's the same thing. So, I mean, you can see it's pretty consistent with it. Okay, I mean, we'll do it again. That's fine. I mean, but there's not a lot of variety with this, you can see. I mean, I could change it to the other side. So this would be, I have the 0.675 molar, that's the higher concentrated amount, and it's asking again, what's the volume of that I need? All right. Oh, no, actually, no, this is backwards. Ha, there you go, you get to see me make mistakes. So, I do have the higher, no, I was right. I'm looking at the wrong numbers. This is the concentrated, so 0.675 times VC equals 0.25. I started looking at this as the concentration, times 0.879. So 0.25 times 0.879 divided by 0.675. I get a volume again, and this is in liters this time, of 0.3, is it 3 sig figs across the board? Yep, 26 liters. Okay. Trying to find one that's a little bit different. Same thing. Same thing. Okay, so this is the last one I'll do because we actually solve for molarity. You're going to see we don't really do anything different with the math, but this one is, we're now finally starting with the concentrated. We have 150 milliliters of 12 molar H2SO4, and I want to dilute it to 2,000 milliliters. What is the concentration of the new solution? So this time, finally, we're solving for something different. We're solving for molarity of the diluted solution, the concentration of it. And so this would be 12.0 times 150 equals MD times 2,000. 12 times 150 divided by 2,000, and that comes out to 0.900 molar solution. So it definitely gets diluted pretty well. So that's the gist of it. I mean, really read for context, plug it in. It's a pretty straightforward formula, and take it from there. Thank you.